Okay, let me start. In this class, am I audible now? Hello?
Yes, sir.
Yes, sir. Yes.
Okay. So in this class, I will talk some topics on physical chemistry. And first, I am telling you what is the syllabus of this. The first I'll start with, okay, I have not shared the screen, I think. Hello. Okay. So first I'll start with thermodynamics.
Yes, sir.
In thermodynamics, there are first law, there are second law, and also some more topics I will cover. And after that, I'll start electrochemistry. Within one or two classes, I will briefly summarize that portion which is included in your syllabus, that electrochemistry part. Then chemical kinetics. And last, adsorption and catalysis. Okay. So some of these topics, that is when I will go through individually, you will see some of the topics you have already gone through in your class 12 standard. Those things will be recapitulated, and also I will talk some extra. Different numerical problems we will solve. And I have already shared you the study materials for thermodynamics part in your this that is MS Team. You can see that. Apart from that study material, I will strongly suggest you should go through any one of the following books, that is either Physical Chemistry by P.C. Rakshit or Physical Chemistry by P.W. Atkins or K.L. Kapoor. For K.L. Kapoor, there are 6 volumes. Thermodynamics you will get in volume number 2. Chemical kinetics you will get in volume number 4. So chemical kinetics and adsorption catalysis. This will be in volume number 4, I suppose. So any one of the books, P.C. Rakshit or Atkins or K.L. Kapoor, any one of the books you should go through, because all individual topics it is not possible for me to tell. You know, there are very limited number of classes. So in addition to that study material which I have shared with you and the whatever I will discuss in this online class, and after all I think within 1 month you will also come here, then we will talk in offline mode also. In addition to all those things, you should go through any one of those books. Okay, so now let us start with thermodynamics. The main concept you already know in your class 11. Thermodynamics, it deals with interaction of one body with another. If I consider two different bodies, so how they interact with each other in terms of heat and work. Now initially it was heat, but later on it was shown that heat is nothing but one form of energy, and hence in thermodynamics all types of energy and work, interaction between two bodies in terms of energy and work, this is the science of thermodynamics. How two bodies interact with each other in terms of any form of energy and work. So just in a nutshell, if I tell you that it actually has 0th law, first law, second law, third law. What is 0th law? Do you have any idea what is the 0th law in thermodynamics? Anyone? 0th law actually gives the concept of heat and temperature. It tells that suppose this is body 1, this is body 2, this is body 3. Three different bodies are there. If body 1 and body 2, if these are under some thermal equilibrium, suppose 1 and 2 are under thermal equilibrium. Thermal equilibrium, what does it mean? That means body 1 and body 2 have same temperature. Same temperature. That is called thermal equilibrium. Now, if the body 1 and another body 3, if this also maintains the thermal equilibrium, that is same temperature, then body 2 and body 3, these two will automatically maintain the thermal equilibrium. That is, if these two bodies have same temperature and these two bodies have same temperature, then automatically these two bodies will have the same temperature. Thermal equilibrium means the same temperature. So this is the concept, and on using this concept, actually thermometer has been devised. In thermometer, 0 level and 10, that is in Celsius degree, it is 0, it is 100, in Fahrenheit it is something else. But whatever it may be, that scaling has been done following this 0th law concept. That is, when your mercury column, it is in contact with ice, that is some thermal equilibrium has been maintained, and the particular position of the mercury column, that is designated as the 0 sign. And again, when the mercury bulb is under equilibrium with boiling water under atmospheric pressure, then your column will rise, it will stand at a particular position, and we define it the term 100. In that way, thermometer has been devised following this 0th law. Okay. Apart from 0th law, now we will discuss first law. But before starting a first law, we require to define some particular terms. You are familiar with all those terms. Simply it is a recapitulation. What do you mean by system in thermodynamics? Suppose you have taken a glass of water and you want to measure what is the temperature or composition of that water contained in the glass. So here, this water will be acting as a system, because this is the interest of you of the whole universe. No other thing you are interested of. You are interested only on the water which you have taken in this glass vessel. That is a part of the universe under investigation. That is a small part of the universe under investigation. That is under which you are interested to, on which you are interested to. That is defined as the system. And the rest of the universe which can interact with your system in terms of heat and work, that is called surrounding. I'm again telling, the rest of the universe which can interact with your system in terms of heat and work, not only heat, that is energy and work, that rest of the universe is defined as the surrounding. Obviously, beyond surrounding, if you consider anything which is beyond the surrounding, suppose this particular point, can it interact with your system? The answer is no. Because if it can interact with your system, then this should also be included in your surrounding. Anything which can interact with your system in terms of energy and work, that is included in the surrounding. Thus, outside your surrounding, there is nothing which can interact with your system. Hence, system plus surrounding, these two constitutes the universe. System and surrounding, these two constitutes the universe. Beyond the universe, there is nothing which can interact with your system. Okay. Now, in between your system and surrounding, there are bounded. In this particular case, the glass wall, this is the boundary. But there are many instances, practical instances, where the boundary is actually not real, but imaginary. And also, your surrounding, it is also, obviously, if your boundary is imaginary, then also your surrounding cannot be defined precisely. For example, suppose you have taken a piece of burning coal. The coal is burning, suppose. The heat is coming out. Heat is coming out everywhere. But is there any real boundary? There is no real boundary. Similarly, is your surrounding is well defined in this particular case? The answer is also no. Because if I tell you, what is the temperature of surrounding here? So if you measure the temperature at this point, the temperature will be high. If you measure the temperature at this point, temperature will be lower than this point. In that way, your surrounding cannot have a well-defined properties. That's why surrounding itself is not well-defined. These are some consequences. I will explain you later on. So apart from this, real boundary and imaginary boundary, a boundary can be diathermal or diathermal wall or diathermal boundary. Through a diathermal boundary, heat can pass. Heat are allowed to pass between the system and the surrounding. Simply consider this one, glass vessel. Through a glass vessel, heat can pass through the system on the surrounding. From the surrounding, heat can go inside. Similarly, from inside, heat can come out. The glass vessel, it is an example of diathermal boundary. And another boundary that is called adiabatic boundary or adiabatic well, where heat is not allowed to pass between your system and surrounding, just like thermoflux. Thermoflux in ideal case, obviously no thermoflux is ideal. In all type of thermoflux, there will be a loss of heat after prolonged use. But in any case, ideally, a thermoflux should be an example of adiabatic boundary. or your tire, rubber material, it is a very good heat insulator. But again, if you see, it is not very good in the sense, after a prolonged use, you will see your tire is very heated up. That means heat is coming out. Anyway, but just for a short duration of time, when your use is not for a prolonged time, you can assume that these are some examples of adiabatic. Now, what is the property of the system? Property are some thermodynamic functions. These are some thermodynamic functions by which one can define the state of the system. That is, properties are those thermodynamic functions by which one can define the state of the system. Suppose temperature, pressure, composition, density, energy, heat capacity. These all are those thermodynamic functions by which one can define the volume, define the state of the system. Just in this example, suppose the temperature of the glass, that is the temperature of the water contained in the glass, is 10 degrees centigrade. It is in a particular state. Now, if you give some heat from outside, its temperature will increase, and let the final temperature is 20 degrees centigrade. Then I will say that now your system is in some different state. 10 degrees centigrade corresponds to, if it corresponds to state 1, then 20 degrees centigrade will corresponds to state 2, just a different state. So in that way, this property, that is those thermodynamic functions, define the state of the system. Now, a property, we can define it in various ways. Property may be a state function. It may be path function. In another term, property can be defined by intensive property and extensive property. Okay. So what are the intensive properties? You already know. Intensive properties are those thermodynamic functions which does not depend on the amount present in that system or mass of the system. That is the intensive property. Like temperature, density, then molar heat or molar enthalpy, molar free energy, whatever it may be, then molar heat capacity or specific heat capacity. These all are intensive property. This does not depend on the mass of the system. But extensive property, that is mass, volume, then your only energy, only heat capacity, that is total heat capacity. These all are extensive property. And the ratio of two extensive properties is an intensive property. Density. Density is nothing but your mass by volume. That is the density. Molar heat capacity. That is heat capacity divided by number of moles. Specific heat capacity. That is the heat capacity divided by mass of the material. Normally it is contained by 1 gram. Specific heat capacity unit is calorie per gram. In SI unit, it will be joule per kg. That means you have to divide the total heat capacity by the mass of the material. Now, state function and path function. There are some thermodynamic functions which depend only on the state of the system. Suppose temperature, pressure, volume, composition, these all are state functions. At a particular state, it has some particular value. And if you consider a cyclic process, then after several intermediate steps, if it comes back to its initial state, it will have the same value. That's why it is said that if a state function is x, then the total change for the whole cycle for that state function x, that is equal to 0. This is a very important concept for state function. That is the total change of any state function for the whole cyclic process, that is equal to 0, because the system is coming back to its initial state. But path function is slightly different. Suppose I have taken some amount of water here. Here temperature is T1. That means it is under state 1. Now I want to increase the temperature of the system at T2, where T2 is greater than T1. Obviously, it is state 2. That is temperature, it is a state function. When it has a particular value T1, I am defining the state by state 1. When the temperature is T2, I am defining the state as state 2. Now, I can carry out this transformation by different paths. Path 1, path 2. In path 1, suppose I have put a Bunsen burner here. When I am using a Bunsen burner, that means heat is going from the surrounding into your system. And as a result, ultimately temperature will be increased from T1 to T2. That means in path 1, heat is positive. Heat positive means the convention is Q positive means the system is absorbing heat. And when the system will absorb heat, internal energy of the system will increase. Internal energy U of the system will increase. This is the sign convention. Q positive means system is absorbing heat, and as a result, internal energy of the system will increase. In path 2, a different path, we can use a padded wheel, some mechanical padded wheel we can incorporate here. There are some wheels. There is a weight here. With up and down of this weight, this wheel will rotate. That is mechanical stirring. Simply you can consider as a mechanical stirrer kind of thing. The weight is coming down and going up, and as a result, this stirrer will rotate. That means you are doing some mechanical work. W is positive. W positive means the surrounding is doing some work on your system. Surrounding is doing some work on your system. And again, as a result, when surrounding will do some work on your system, your internal energy of the system will increase. That is, when Q is positive, U is positive. Increase means internal energy is positive. When W is positive, W positive means surrounding is doing work on your system. Then also internal energy will increase. That is, internal energy of the system is positive. So you can see in path 1, you are not doing any mechanical work, that is W equal to 0. In path 2, you are not doing any, you are not giving any heat. Hence, Q, W, these two are actually depends on the nature of the path by which you are transforming the state from to state 2. That's why Q and W, these are called path function. But internal energy, temperature, these all are state function. In fact, following this, we can now define your first law of thermodynamics. That is total change in internal energy. That is the Q plus W. This is the mathematical form of first law of thermodynamics. Delta U is equal to Q plus W. For infinitesimally small change, then du is equal to dq plus dw. But for a considerable amount of change, then del u, that is total q plus total w. And mind it, when q is positive, that means system is absorbing heat, del u will be positive. W positive means surrounding is doing work. Then also your internal energy will increase. So obviously, if W negative, what does it mean? This means system is doing work on the surrounding. System is doing work on your surrounding. And when a system does some work, its internal energy of the system will be decreased. That is, it will also be negative. Internal energy will decrease. That is, the change will be negative. So this is the first law of thermodynamics. What is the statement? If you consider a, okay, before that, again a system may be an open system, system may be closed system, system may be isolated system. What is open system? Both heat and matter can be exchanged between the system and the surrounding. Between the system and surrounding, both heat and matter can be interchanged or exchanged. That is called open system. Our body, it is an example of open system. Suppose water pump. Those you are all engineering students mostly. When you, particularly mechanical, electrical or metallurgy, those people when, or civil, when they will go to their respective streams, they will actually start with different, particularly chemical engineering, they'll start for different type of pumps. Those pumps are example of open systems. Our body biological system, that is also an open system. Both heat and matter can be exchanged between the system and the surrounding. For closed system, heat can be exchanged, but matter cannot. Matter cannot be exchanged between the system and the surrounding. That is the closed system. An isolated system, neither heat nor matter can be exchanged between your system and the surrounding. For example, if we consider the universe, because as I told you, everything which can interact with your system, that is incorporated in your surrounding, and system plus surrounding, that is the universe. Hence, beyond the universe, there are nothing which can interact with your system in terms of heat or matter, whatever it may be, there are nothing which can interact with your system. As a result, universe is regarded as an isolated system. Now you can see, for an isolated system, Q0 and no matter is exchanged, Q0 and also there is no exchange of matter, that means W will also be equal to 0. Under this condition, if there is no heat change or change in matter, your W work will also be equal to 0. There will be no work done on the system or work done by the system for an isolated system like universe. Then, what about the change of internal energy for an universe? There will be no change of internal energy. That is, internal energy of the universe is conserved, or simply energy of the universe is conserved. That is the statement of first law of thermodynamics. Energy of the universe is conserved. Later on, it has a slight modification, that energy plus mass of the universe is conserved, because you know mass and energy are interchangeable, they are interrelated. If you destroy some amount of mass, you will get energy. That's why it is slightly modified, the statement. The total energy and mass of the universe are conserved. That is the statement of first law of thermodynamics. Now, whatever example or whatever thermodynamics we will learn in this class, in this first semester class, that will be applicable for closed system. That means we will not consider any exchange of mass between your system as well as surrounding. Only heat. Heat is nothing but one form of energy. That is, exchange of heat, that is allowed. Exchange of different forms of energy is allowed between your system and surrounding. Exchange of different forms of energy is allowed, but no exchange of matter between your system and surrounding is allowed. So whatever thermodynamics we will study in this particular semester, that will be applicable for closed system. When you will go to your higher semester, you will start the open system condition. Just as I told you, your pump, different type of pumps, those are example of open system. There is both the exchange of energy as well as exchange of matter between the system and the surrounding. Just for example, if you consider PV is equal to nRT, this equation also is applicable for closed system. I can give you very easy example of it. Suppose you are inflating a balloon. Suppose a balloon, you are inflating it. When you are inflating it, that means you are giving some matter, some air is going inside. And what is the effect of that? The effect is both volume is increasing as well as pressure is increasing inside that balloon. But following this equation, P should be various 1 by V at constant temperature. But in this particular case, you can see when you are inflating a balloon, both volume is increasing, pressure is increasing, only because in this case, it is not a closed system. You are incorporating some amount of matter from outside. Air is going inside, that means you are pushing some matter inside. That is, in this case, it is an open system. That's why if V is equal to nRT, this relation will be no longer valid in this case. Okay. Now, before discussing more of first law, there are different processes. A process may be isothermal. Isothermal, you know, temperature is constant. It may be adiabatic. That is Q, heat is constant. It may be isochoric. Volume is constant. Isobaric. Pressure is constant. Isochronic process, that is the pump, though it is an open system, but anyway, pump, it is an example of isochronic process. Or your compressor in your refrigerator, that compressor, or engine of the automobile, these all are example of open system and all are actually isochronic in nature, because these have fixed volume. Similarly, isobaric, whatever biological reactions are occurring in our body, these are happening under normal atmospheric condition. These are isobaric reactions. And when it is isothermal, isothermal means there should be diathermal wall. That is, through the boundary, heat should be exchanged. If through the boundary heat cannot be exchanged between your system and surrounding, temperature cannot remain the same. Temperature of the system cannot remain constant. In order to maintain a constant temperature of your system, there should be a diathermal wall. And for an adiabatic process, your boundary should be adiabatic wall. As a result, what will happen? Suppose you have considered an insulated system. This is completely insulated, suppose. That is a adiabatic boundary, suppose you have to. Now, and obviously it is a closed system. Closed system with adiabatic wall. Now, if you compress it, if the volume decreased, then there will be, what will happen? There will be more number of collision among your molecules, which is trapped inside the lesser number of volume, less volume. As a result, temperature will increase. That is, for adiabatic compression, temperature increases. But in the same system, that is a closed system with adiabatic wall, if I increase the volume, if I move the piston upward, then volume will increase. Volume increase, that means system is doing some work. Now, for any amount of work to do, some energy is required. But there are adiabatic wall, hence from the outside, it cannot take up any heat. Then from where it will take up the energy for the expansion process? It will utilize its internal energy for the expansion process here. That means at the expense of the internal energy, volume will be increased in this adiabatic process. What will be the result? Adiabatic expansion, as it is utilizing its internal energy, its temperature will drop. So this is the case. For adiabatic compression, temperature will increase. For adiabatic expansion, temperature will decrease. Actually, when you are compressing it, that means you are doing some work from the outside, surrounding is doing some work. And as it is an adiabatic wall, heat cannot go outside. As a result, your internal energy will increase and it will be manifested by increase in temperature. Similarly, in case of adiabatic expansion, expansion will happen by the expense of its internal energy of the system, and it will be manifested by the decrease in temperature. Apart from these four, another cyclic process which I have already told, and for any state function x for the whole change, it will be equal to 0 for a cyclic process, where x is state function. Now, apart from all those, there are very two important processes, which is reversible or equilibrium process. Another is irreversible or spontaneous process. You should listen to it very carefully and you should understand by yourself. If you have any doubt, you can ask me. Am I audible? I am not getting any.
Yes, sir. You are audible.
Okay.
Yes, sir.
Yes, sir.
Suppose I have taken a cylinder and this is fitted with a frictionless piston. Now, there is a particular opposing weight here. This opposing weight is giving you a pressure, opposing pressure. And under this opposing pressure, the position of your piston is particularly residing at this particular point. And the volume inside is V1. Well, there are some gas molecules. And everything, it is closed system. There is no mass transfer is allowed. Now suppose I want to increase the volume from V1 to V2. So let this is V2. How we can increase the volume? Obviously, we have to reduce or decrease the opposing pressure. That is, we have to put a lighter weight. So directly suppose I have put a lighter weight W2. W2 is giving the opposing pressure P2. P2 is less than P1. The piston will instantaneously go up and increase in volume will be from V1 to V2. Instantaneous or spontaneous process. Simply, I am replacing the opposing weight W1. Suppose initially it was 1 kg weight. I have replaced this by a 500 gram weight. W2 is lower, 500 gram. Instantaneously, piston will go up. This is a single step process by which you are increasing the volume. Now I can increase the number of intermediate steps. Initially there was 1 kg, final 500 gram. So first I have replaced with a 750 gram of weight, and then I have put 500 gram of weight. That means there will be some intermediate step. Initially increment will be this, and then this. That is now a two-step process. In that way, I can increase the number of intermediate steps. Similarly, during compression, suppose final weight was 500 gram. If I put directly 1 kg weight, the piston will at a one go, it will come from the final position to initial position. But first suppose I have put 750 gram, piston will come midway, and then the piston will come this way. So in that way, during compression also I can increase the number of intermediate steps. During expansion, during compression, I can increase the number of intermediate steps. Now, as long as there are finite number of intermediate steps, I will call you an irreversible or spontaneous process. Whatever may be the number, it may be 1, it may be 1 lakh, whatever may be the number, as long as it is finite number of intermediate steps, it will be irreversible or spontaneous process. Why? Why it is spontaneous? Why it is irreversible? I will come one by one. Now, if there are infinite number of intermediate steps, infinite number, either expansion or compression, then that process will be a reversible or equilibrium process. Why? Now I will explain. See, if there are infinite number of intermediate steps, what does it mean? That means your opposing pressure will be reduced by infinitesimally small quantity. That is, the opposing pressure will be the initial pressure minus infinitesimally small amount. This is during expansion. That is, I am decreasing the opposing pressure by infinitesimally small amount. Similarly, during your compression, your opposing pressure will be your initial pressure plus dP. That means I will increase the pressure by infinitesimally small amount. Okay. So if I will do in this way, that is, if I decrease or change, I am not using the term increase or decrease, I am using the term change because this is applicable both for expansion and compression. The sign may be positive, sign may be negative. So if the change is infinitesimally small amount, then what will happen actually? And if there is finite number of intermediate steps, then what will happen? Why the difference is coming? Why in one term I am calling it a reversible or equilibrium, in another term I am calling irreversible or spontaneous? The change will be if there are infinite number of intermediate steps. That means if the opposing pressure is changing by very, very small amount, infinitesimally small amount, then in any intermediate step, the system, this is the main particular point, the system will get sufficient time to maintain thermal and mechanical equilibrium with the surrounding. I'm again telling you, if the process is truly reversible or equilibrium process, then there will be infinite number of intermediate steps during any change in state. And in that case, the changes are so slow, or changes are infinitesimally small, that during each intermediate step, the system will get sufficient time. System will get sufficient time to maintain thermal and mechanical equilibrium with the surrounding. What does it mean? That means during each intermediate step, the temperature of your system, temperature of your surrounding become equal, thermal equilibrium. Temperature of your system, temperature of your surrounding will become equal. Mechanical equilibrium means temperature of your, pressure inside the system and the opposing pressure, it will be the same. That system will get sufficient time to maintain thermal and mechanical equilibrium with the surrounding. That is the internal temperature, external temperature will come to an equilibrium value. Internal pressure will become the external pressure. That is, pressure will maintain the equilibrium condition during each intermediate change. Because each change is so slow, the system will get sufficient time to maintain this equilibrium. That's why it is called equilibrium process. That system and surrounding is maintaining thermal and mechanical equilibrium. Internal pressure will be equal to external pressure, temperature inside and outside will be the same. But if it is not infinitesimally slow, if there are finite number of ways, that is for all practical purposes. Obviously, infinite number of intermediate steps, it is not possible practically. We can approach reversibility by increasing number of intermediate steps, but obviously 100% reversibility cannot be achieved. It is a theoretical process. For any practical process, that should be irreversible or spontaneous. That is, the system will not get sufficient time to maintain thermal and mechanical equilibrium with the surrounding. It is a spontaneous process. Now, what will be the consequence of this? That is, in one case, it is system is maintaining thermal and mechanical equilibrium. And another case, the system is not getting sufficient time to maintain the thermal and mechanical equilibrium. What will be the difference of fate for these two processes? Suppose, I will take just 5 minutes more. Suppose a particular intermediate steps during equivalent intermediate steps. This is during expansion, this is during compression. This is the equivalent intermediate steps. Now, if it is a truly reversible or equilibrium process, during expansion, suppose during this particular intermediate step, the system is absorbing dq amount of heat from the surrounding. Then, during the equivalent intermediate step during compression process, if both expansion and compression, if both are reversible, then during this equivalent intermediate step, the system will discard same amount of heat to the surrounding in that equivalent state. Similarly, during that, if the change in volume is dV, then here the change in volume will be minus dV. Okay. That is, change in volume means the amount of work done by the system is dW, and during compression the amount of work done by the surrounding, it is also dW on the opposing sign. Here dW, sorry, here the dW will be negative actually, because your system is doing work and here the surrounding is doing work. That means here the dW will be positive. So this is the case for a reversible or equilibrium process. Then for a reversible process involving PV work only, what is the total change of heat for the whole process, whole expansion plus compression? It will be 0. What will be the total change of dW? It will be also equal to 0. This is applicable if the process is a reversible process involving pressure volume work only. Mind it, W or Q, these are path function, but still it is obeying that relation which is applicable for a state function. As I told you, for a state function, this is applicable for any process, either reversible or irreversible. If x is a state function, this is applicable both for a reversible as well as an irreversible process. But if it is a reversible process involving pressure volume work only, then the same type of relation is applicable for path function also. Obviously, for a irreversible process, this is not applicable. So this is the difference between a reversible system and an irreversible system. Reversible means equilibrium, that is, it is maintaining thermal and mechanical equilibrium with the surrounding only because it is getting sufficient time to maintain that equilibrium. For an irreversible or spontaneous process, it will not get sufficient time to maintain thermal and mechanical equilibrium. So one thing you can see that the property of a path function can be converted into a property of a state function by applying certain conditions. Here, what are those conditions for W and Q? The process should be reversible and there should be PV work only, pressure volume work only. Then property of a state path function is being converted to that which is applicable for a state function. This is very, very common in mathematics. In mathematics, state function, that is called exact differential. Path function, inexact differential. Inexact differential can be made exact by incorporating certain conditions. This is very common in mathematics. So that is some practical application you can see in thermodynamics also. Here I am stopping today. Next day I will start from the first law and I will proceed accordingly. Okay. So I have already shared you that note. Whatever I have talked, it is also recorded.